Alright, so in section 6.4, we're going to talk about properties of logarithms. First, what we want to talk about is that we can break down exponential terms like we saw in section 1.2 in the following way. If I had 2 to the power of 2x plus 3, I could break that down with this multiplication property, and I could break it down even further with this power to a power rule, and I could keep it going if I wanted to. But the whole point is that exponential terms are very soluble, and so are logarithmic terms. We have a theorem below that's going to categorize all three rules that we'll be using in this video. So I'm going to consider a real valued base that's positive and not equal to 1. I'm going to let x and y be positive numbers, and let r be any real number that I want. The first rule that we get is called the product rule. This says that if I have the log base a of x times y, this can split up as log base a of x plus log base a of y. Second, we have the quotient rule. When I'm taking the log base a of a fraction x divided by y, this splits up as log base a of x minus log base a of y. And last, we have the power rule. This says that when I'm taking log base a of x raised to the r, that r can come down and out front and get the expression r times log base a of x by itself. So the point here is that if I'm looking at an algebraic expression with a lot of products and fractions and exponents, these logarithmic functions can help me break that down into smaller pieces. And even though these log terms will be involved, I've essentially got a wider collection of terms that are easier to deal with on their own right. Right, so everything on the left-hand side is something that we would refer to as compressed, and everything on the right-hand side is something we would refer to as expanded. And the problems that we're going to get, they're going to tell us to either expand or compress a logarithmic expression. So it's good to know what's what. So we'll start by expanding the following two examples. Begin with log base 4 of 64 times x cubed times the square root of y. First, start by rewriting everything inside to an exponent. 64 can be expressed as 4 to the third, then we have x to the third as it already was, and let's write that as y to the 1/2. Now real quick, I could have written 64 as 2 to the 6th power, but because I have a log with a base of 4, I chose to make the base of that exponential term inside match. It's very good to do that whenever possible, because you never know what might cancel in the future. Right, so I have a product of things inside, so the first thing I'm going to do is use the product rule. This can be expanded as log base 4 of 4 to the third plus log base 4 of x cubed plus log base 4 of y to the 1/2. Now, since everything inside is a single term raised to a power, I can use the power rule. That means that I bring each exponent down and out front. I'm going to get 3 times log base 4 of 4 plus 3 times log base 4 of x plus 1/2 times log base 4 of y. Now it actually turns out that that first term can be simplified just a little bit further, and I'm going to leave it to you as an exercise to think about it, but you can also refer to the notes to see how that 3 times log base 4 of 4 simplifies even further. But this is how we expand logarithmic expressions. Whenever I'm taking the log of a big expression like the one we had here, I can use that log to just help dissolve and split it apart to where I have a lot of terms, but each term on its own right isn't too bad to look at. Let's look at another example. Consider log base 2 of the square root of x squared divided by x squared times z to the 4th. Now this is a lot, but that's the whole point of these logarithmic expansion properties, is that I can take this gross expression and expand it to make it look a little bit more user-friendly. Let's begin by getting rid of that radical notation and replacing it with this entire quantity raised to the 1/2 power. When I've got that, that's going to let me use the power rule so I can bring that 1/2 down and out front. This is going to give me 1/2 times log base 2 of the quantity x squared divided by y squared times z to the 4th. We still got some work to do, but this is already starting to look a little bit nicer. I've at least gotten rid of the radical part. But now the quantity inside my log is a fraction, so we're going to use the quotient rule. This is going to give me 1/2 times the whole quantity, log base 2 of x squared minus log base 2 of y squared times z to the 4th. Now we got to be really careful about this because that 1/2 has to be multiplied by this entire difference, not just the first term. That's why I have an additional set of parentheses covering the log base 2 of x squared and the log base 2 of y squared times z to the 4th. Looking at the second log term, I'm going to use the product rule to break up that log base 2 of y squared times z to the 4th. This is going to give me the expression 1/2 times the quantity log base 2 of x squared minus the secondary quantity log base 2 of y squared plus log base 2 of z to the fourth. Notice that that negative has to apply to everything inside that product rule expansion term. Otherwise, we're making mistakes. We can't drop negatives in this place. But now that I no longer have any products or quotients inside my logs, I can use the power rule to bring everything down and out front. This gives me 1/2 times 2 log base 2 of x minus 2 log base 2 of y minus 4 log base 2 of z. Now I can finally distribute that 1/2 that's been lingering out front to get the final expression of log base 2 of x minus log base 2 of y minus 2 log base 2 of z, and we're done. So like I said, even though the expression that we begun with was pretty gross to look at, the final expression ultimately is preferable because we don't have any fractions, radicals, or quotients. We just have a string of logarithmic expressions. I do want to address a very common error that can be made when using the product rule or the quotient rule. If I just had the term negative log base a of x times y, and I wrote it as negative log base a of x plus log base a of y, this would be incorrect because that negative applies to the entire thing. So I have correctly used the product rule, but I forgot to distribute that negative sign everywhere that I should have. What I should have done is written that negative log base a of x times y is equal to negative times the quantity log base a of x plus log base a of y. That's me using the product rule with the plus part. But then I distribute my negative and I get negative log base a of x minus log base a of y. And that's pretty much what I was doing in this underlined portion here. And the best way to really be careful about not dropping negatives is put up parentheses every time that you have to expand something, especially when negatives are involved. Alright, so this next set of problems basically goes in reverse order. We are now going to compress the entire expression into a single logarithm. So this is basically the backwards version of what we just did. Start with 3 times log base 4 of 2x minus 2 times log base 4 of x plus 1. The first thing I'm going to do is use the power rule, but in reverse. I'm going to bring those coefficients 2 and 3, and I'm going to bring them inside their logarithms. This is going to give me log base 4 of 2x raised to the third minus log base 4 of x plus 1 quantity squared. Now let me simplify the terms inside. By applying those powers of 3 and 2, I'm going to get log base 4 of 8x cubed minus log base 4 of x plus 1 squared. I don't need to expand the polynomial in the second term. I can just leave that as x plus 1 squared and call it a day. But I can apply that 3 to the first term because it's a little bit easier to work with. Now that I have a difference of logarithms, I can use the quotient rule. The quotient rule says that turning a difference into a fraction means that the first term, the one before the minus, is going to be in the numerator. The second term, the one after the minus, is going to be in the denominator. So this is going to transform into log base 4 of 8x cubed divided by x plus 1 quantity squared. And this completes the problem. We have a fully compressed single logarithmic term. In our next example, look at 1/2 times natural log of x minus 3 times ln of y plus ln of 3. I know that my terminology in there switched up, but whenever I see the natural log function, it's generally common to abbreviate it as just saying ln instead of saying the natural log function every time, because it's understood what that symbol means. Right, so the first thing that I'm going to do is use the power rule in reverse. I'm going to bring each one of these coefficients inside their logarithms. This is going to give me ln of x to the 1/2 minus ln of y cubed plus ln of 3. In the previous problem, it was pretty clear that I should have used the quotient rule because I had two terms being subtracted from one another. But here I have three terms happening at once, one with a minus and one with a plus. The easiest way to remember how to handle this is to remember our order of operations. I have pluses and minuses, which go from left to right. So this means I'm going to take care of those first two terms, ln of x to the 1/2 minus ln of y cubed first. And I'm going to transform that, again using the quotient rule, as ln of x to the 1/2 divided by y cubed plus ln of 3. I've only got one more operation to take care of, and I'm going to combine these two terms using the product rule because I see a plus. Thus, I'm going to get a final answer of the natural log of 3 times the square root of x divided by y cubed, and we're done. This log is fully compressed into a single logarithmic expression. In this next slide, we're going to look at a slightly harder problem, but we're going to treat it like we're solving a puzzle. I have 4 raised to the 2 times log base 2 of x minus log base 2 of y. Now obviously, this is kind of a lot to look at, so it's really not clear how to start. But let me present it to you in the following way. The worst thing about this problem is clearly that exponent. So for a moment, I'm going to look at just the exponent by itself, and I'm going to see if it simplifies. You can kind of think of this like scratch work, because this problem would be a lot nicer or a lot easier to look at if that exponent had fewer terms and was just overall a bit nicer. So again, isolate the exponent by itself and see if it simplifies any. We have 2 times log base 2 of x minus log base 2 of y. We're going to compress this into a single term. So first we'll use the power rule, and then the quotient rule to get log base 2 of x squared divided by y. So now that it's compressed, I can go back to the original expression and replace that power of 4 with log base 2 of x squared divided by y. This at least gives me less to look at, which is ultimately the nice thing. Alright, well the exponent is smaller and has fewer characters, but how exactly did that help us here? It doesn't look like anything is just going to magically cancel right off the bat. And yeah, nothing does cancel right now. However, I have an exponential term whose base is 4 and a logarithmic term whose base is 2. We know that we can transform that base of 4 into 2 to the second power. And the reason that's going to help us is because of the following cancellation rule. Remember that a raised to the log base a of x gives me x itself. So if I could transform that 4 raised to the log base 2 of stuff into an expression that has 2 as the main base of the exponential expression, I can use this cancellation law. The whole point is to make all bases in the entire problem look the same. So let's go ahead and replace 4 with 2 squared, all raised to the log base 2 of stuff. And now I'm going to multiply those things together because I know that a power to a power means multiplication in the exponents. When I do that, this will give me 2 raised to 2 times log base 2 of x squared divided by y. And now I'm going to use the power rule to bring that coefficient of 2 inside the exponential term, because that's exactly the thing that will let me use my cancellation law. So when I bring that 2 in, I'm going to get 2 to the log base 2 of stuff. Finally, I have canceling bases. The exponential and the logarithmic expressions both cancel out, and I'm finally just left with the fraction x to the 4th divided by y squared, and we're done. The last topic of the slide is something that's a little bit more practical. Most physical calculators will have a log or an ln button. Normally the log button by itself refers to the common log, which is going to be log with a base of 10. And ln, like we've been saying, is the natural log, which is the log with a base of e. You'll notice that the iPhone calculator, if you tilt it on its side, will have both the ln button and the common log button, but it actually tells you that you have a log base 10 function. But depending on the calculator, you could have something a little bit different. But typically you just type in one of these buttons and you're given an open set of parentheses. You type in the number that you want and you hit enter. And if you're interested in the programming side of things, Python has a math package that you can import, which will let you use the log function as well. But it's a little bit backwards here. If you type in math.log of x, Python understands this by default as the natural log function. But this function is actually overloaded, so you can do the second line of code here that would have log with an input of x, and the second argument is an a, where that is establishing your base. So yeah, if I had a programming language, then certainly I should be able to use a log with any base that I want. But if I'm using a simple calculator, maybe I'm restricted to just the common log or the natural log. But that's not going to be so good if I need to compute something like log base 7 to the 21, for instance. Because how on earth do I get those if I don't have that function or that button available in my calculator? What we do for that is we use something known as the change of base formula. Suppose that I need log base b of x, but I'm stuck in log base a. So the right-hand side is what I would throw into a calculator. So if I'm stuck on the natural log function or the common log function, that base of a on the right-hand side doesn't matter anymore. So like I said, if I needed log base 7 of 21 and I'm stuck, let's say, in the natural log mode, then I can type into my calculator ln of 21, the input value, divided by ln of 7, the desired base, and what I'm going to get is 1.564, which is exactly what my log base 7 of 21 would come out to. And this works in whatever base I'm stuck in. because if I wanted to use the common log function, I could still compute log base 7 of 21 as common log of 21 divided by common log of 7, and I get the same number. So again, the point of this slide is to give you sort of a practical idea of how I can compute different logs when I have a calculator that might not allow for the different log bases that you might encounter in this class. Okay, well thank you for watching, and join us in our last video of the chapter on logarithmic and exponential equations.